I'm Matt Harrington. I'm an EFCO field service rep, and today we're going to talk about understanding pressure and pour rates. Concrete pressure is invisible but powerful. When it's not controlled, it can push a formwork system beyond its limits. At EFCO, we know safe, injury-free wall pours depend on more than equipment strength. In this video, we'll explain how concrete pressure works, how to calculate and follow correct pour rates, and the essential steps crews should follow to keep every pour safe and efficient. Fresh concrete behaves like a liquid. The deeper it gets, the greater the pressure at the bottom. However, concrete is more than twice as heavy as water, so the pressure builds faster and carries more risk. One of the most important facts to remember is that the wall width doesn't affect pressure, only height does. A 1 foot wide, 12 foot tall wall exerts the same pressure as a 6 foot wide one at the same height. This surprises many, but it's critical knowledge for safe construction. Think of it like buckets of water. It doesn't matter how wide the bucket is, the pressure at the bottom depends only on how deep the water is, not the size of the opening at the top. If you hold a tall bucket and a short bucket side by side, the deeper water in the taller bucket creates more pressure at its base. Fresh concrete behaves in the same way. Its weight and depth control the pressure, not the wall's width. That's why formwork must always be designed and checked for the height of liquid concrete. Pressure builds with depth, no matter how wide the wall is. Keeping this principle in mind helps crews avoid overloaded forms and the costly failures that come with them. Forms are rated for a maximum pressure, which is defined by the design of the form or the manufacturer. The height of liquid concrete multiplied by the density of the concrete is the pressure that the concrete exerts on the form. At the top, the pressure is 0, but at the bottom, it can reach thousands of pounds per square foot. For example, a system rated at 1,200 pounds per square foot is designed to hold 8 feet of liquid concrete at 150 pounds per cubic foot. If the pour continues adding more height of liquid concrete, the form can bulge or fail. Respecting formwork pressure isn't optional. It's the foundation of safety. The way to stay within the allowable pour pressure of a form is to control the pour rate. Pour rate defines how quickly concrete can rise in a form without exceeding the allowable pour pressure. It's measured in feet per hour and depends on how quickly the concrete mix stiffens from a liquid to a solid, which is driven by temperature and chemistry. During the pour, the concrete at the bottom of the form begins to harden, no longer exerting additional pressure. This allows you to keep pouring at the assigned pour rate, never exceeding the allowable pour pressure. Truck timing is also important. If the trucks arrive from the batch plant too quickly, the urge to pour faster is greater. Do not be afraid to turn away trucks to maintain a safe pour rate. Hot concrete, such as 80 to 90 degrees Fahrenheit, hardens faster, allowing a quicker placement. Cold concrete, such as 40 to 60 degrees Fahrenheit, set more slowly and require crews to slow down. Additives like retarders or plasticizers can also delay setting, which means that the pour rate must be reduced accordingly. Tracking the set time of concrete samples is a good way to make sure you are not exceeding the pour rate. Industry standards such as ACI 347 provide formulas to calculate the safe pour rates and pour times. Work with your project engineer to use these calculations to calculate the pour rate. Now let's discuss how to use pour pressure charts in the erection drawings. Engineers have determined the allowable pour pressure of the formwork. All you need to do is determine the additives in the concrete and its temperature. There are 3 places to find what type of cement and additives are in the concrete: the approved concrete mix design, the concrete order ticket, and the batch plant ticket from the concrete truck driver. While the concrete mix design provides the chemistry for the planning purposes weeks in advance of the pour, it's best to use the batch plant ticket from the driver to check what components are in the concrete. This prevents accidents when the mix design has been changed and the crew has not been informed. Once you have determined the cement type and additives, use the chart to determine the chemistry coefficient that will indicate what line to use on the graph. Next, find the temperature of the concrete by placing a thermometer at least 3 inches into the concrete per ASTM C1064 standards.
Because lower temperature concrete sets up slowly, be careful that you do not confuse the air temperature with the concrete temperature when determining the pour rate. For example, if you use 80 degrees as the air temperature when the concrete is 20 degrees colder at 60 degrees, the chart will give a pour rate that is twice as fast, doubling the pour pressure, leading to a blowout.
Now find the concrete temperature along the bottom of the chart. Go up to the correct chemistry coefficient line and then over to the allowable pour rate. Let's do a quick example. The batch plant ticket shows that the cement is type 1 or 2 and has retarders and fly ash. You go to your chart and find the chemistry coefficient is 1.4. You've taken the temperature of the concrete and find it to be 70 degrees Fahrenheit. Now you go to the chart and find the allowable pour rate is 5.5 feet per hour. The pour rate will also tell you how long it should take to pour the entire wall. Simply divide the height of the wall by the pour rate. 12 feet divided by 5.5 feet per hour equals a little over 2 hours. This information can be used by project management for planning purposes and to monitor and verify that correct pour rates are being used. If the wall in our example was finished in 1.5 hours instead of 2.5, project management knows that the pour rates were not followed. Trying to finish in half the time doubles the pressure, doubling the risk and likely resulting in some kind of failure. Pour rates aren't suggestions, they are limits designed to keep projects safe. Have experienced crew members monitor the formwork and the pour for signs of exceeding the pour rate. Early warning signs are pillowed finishes and bulges in the formwork. The vibration of concrete needs to be closely monitored. Over-vibration can reliquefy solidifying concrete lower in the formwork, causing pressure spikes, bulges, or worse, form failure.
Per ACI, internal vibration should go no deeper than 4 feet.
Self-consolidating concrete, or SCC, adds even more risk because of its extreme fluidity. SCC flows easily into the forms without vibration. Currently, no formulas exist to calculate the pour rate for SCC. Therefore, engineers must design formwork assuming that the whole wall will be full liquid concrete. Other methods, such as monitoring pour pressure with sensors on the face sheet, allow contractors and engineers to design for lower pressures. On-site, the process is straightforward. Check the batch ticket for additives and mix design and determine the chemistry coefficient. Measure the temperature of the concrete itself, not the air. Check the engineered drawings for rated allowable pour pressure of the formwork. Use the ACI equations or pour chart to determine and confirm the safe placement speed. We've seen how pressure builds and how pour rates control it, but knowledge isn't enough. Crews need a process that can apply on every job. The process is captured in EFCO's 8 key steps. 1. Inspect the formwork and confirm all hardware is in place and tight. Loose hardware can cause the pressure from the liquid concrete to be transferred to the surrounding ties and bolts, causing them to be overloaded and potentially fail. 2. Review the concrete mix design and additives. Additives such as air entrainment, retarders, and plasticizers can delay setting. Make sure the paperwork matches what you've ordered from the batch plant. 3. Use the pour rate chart based on the actual concrete mix design and temperature. Concrete composition and temperature will both affect the pour rate. Use the ACI equations or EFCO supplied pour chart to determine the safe pour rate for your project. 4. Schedule truck arrivals to match the safe placement rate. If the truck arrives too quickly, the urge to pour faster is greater, which will result in exceeding the allowable pour pressure of the formwork. EFCO has a video that explains how to calculate the truck schedule based on the pour rate in more detail. 5. Monitor concrete samples. Take samples to monitor and confirm that the concrete is setting up. EFCO has a video that explains this process in further detail. 6. Recalculate if conditions change during the pour. If the temperature or mix chemistry changes mid-pour, recalculate the pour rate and adjust the rate of pour. 7. Place at the planned rate. Avoid over-vibration. Remember, over-vibration can liquefy solidified concrete lower in the formwork. This will increase pressure on the formwork to the point of bulges or worse, failure. 8. Keep experienced crew members monitoring throughout the pour. They will check batch tickets and temperatures, adjust truck timing and pour rate, and keep pressure within the form's rating. They'll catch early warning signs, pillowed finishes, bulges, or over-vibration, and act before a failure. These steps are the difference between safe, efficient pours and costly failures. Concrete placement is more than moving material into a form. It's about controlling powerful forces that aren't visible but must always be respected. Always remember, pressure builds with height, and pour rates keep the pressure in check. EFCO's 8 steps give crews a proven process to follow. backed by our commitment to quality and design, integrity and practice, innovation and problem solving, and super service on every job site. EFCO helps contractors put these principles into action, preventing failures, protecting crews, and delivering safe, efficient results at the lowest in-place concrete cost.